Hello and welcome. This is Vectors Part 2. Now, you already know how to add and subtract vectors in the graphical representation. Let's review that. So, vectors and the graphical representation. Graphical rep, which are basically arrows. So given two vectors A and B, you line them up so that the tail of the second vector is where the tip of the first vector is, and from the tail of the first vector to the tip of the second vector you find your sum, A plus B. Now, there's an alternative way of looking at it, and that is by parallel transporting the second vector. Once you find it like this, you can transport it here so that both A and B start at the same point. I mean, you could view it as A being transported parallel as well, like this. So this way you have a four-sided object, which is called a parallelogram. Okay, so given vectors A and B, if their starting points is the same, you form a parallelogram using the parallel vectors, and you go from the diagonal, from one end to the other. The diagonal gives you the sum. So that's an alternative representation. So given A and some other vector B, you draw these parallel lines and then find the diagonal to be the sum. Okay, and second, we saw how to subtract the vectors in the context of position vectors, remember? But in general, again, given A and B, if you line them up like this with the same point as the starting point, then this vector that goes from A to B, or the tip of A to tip of B, is B minus A. Alright, now these are all fine, but are you going to always draw vectors, draw arrows with rulers, and then measure angles? Because if your goal is to find A plus B, you got to be very precise. I mean, you have to be careful, because when you carry the vectors parallel, you don't want to change the direction. And you want to also make sure that the lengths are the same. Like, look at this two B's that I just draw here. Well, they obviously have different lengths because I wasn't that accurate. But if you want to do it on a paper, maybe you want to use graphing paper and then rulers and protractors, it's not always convenient. So we need a second representation for vectors, which is going to be called the coordinate representation. Coordinate, or component, let's say. Coordinate or component representation. So, what are coordinates to begin with, right? So, remember how we studied dimensions, physical dimensions, like length, width, height? That would be 3D, or in 2D space, which would be a surface, or one-dimensional, just the length. Let's start with one dimension. It's a 1D problem. You can only move right or left. What you do is you pick a point and call it your origin. That's your 0 point. And the numbers on this line will be your coordinates. I'm going to give this a name. I'm going to call this line the X line. And any number to the right of 0 will be a positive X, starting with 1, and then 2, and 3, etc. And if I pick a point to the left of 0, or origin, that would be the negative number, -1, -2, etc. Okay, so by coordinates, I mean this. These are just the numbers along that line, and which I name them X. So if I use 2D, I just need 2 lines, which I call the axes. The X axis and the Y axis. So any point on this 2D plane is uniquely determined by just 2 numbers, because I will have the intersection point as my origin, and my positive y's will be here, 1, 2, 3, etc. And my positive x's will be to the right. So any given point on this xy plane will be a pair of numbers, x and y, basically. So I pick a point here, let's say right there, point P. Point P here, I find the projection of this point onto these 2 axes, and I call them x and y. In this case, it'll be 3 and 2, right? Point P, x, y. Actually, I could be on the negative side as well. So let's extend these lines again. These for negative y's, and this line here for negative x's. So a point over here, okay, call this point Q. This would have a negative x, a negative number, but a positive y. We call these quadrants. The first quadrant, the second quadrant. And now we have a third quadrant here, where both x and y are negative. And then a fourth quadrant. These are called quadrants. And this way of describing points on the xy plane is called Cartesian coordinates, or rectangular coordinates. The reason we call it rectangular is because of this rectangle that is formed here. Okay, any point on this plane will correspond to a rectangle, you know, so we call these rectangular coordinates, or Cartesian. Cartesian coordinates, named after Descartes, a French mathematician and philosopher. All right, so very basic. Of course, you can do it in 3D as well, right? In 3D, you will have 3 axes. Just give me a second. I had to let the cat out. All right, so in 3D, why don't you use, of course, in 3D, you have to visualize it, but when you're drawing it on paper, a paper is a 2D surface, so you have to use your imagination and drawing skills a little bit. So you start with the 2 axes that you already have, which are x and y. Now the third axis will be perpendicular to the plane that is formed by x and y. So think of it as an axis that is coming out of the monitor or from the paper, which I will show as this line here, and I'm going to call it Z. All right, so x and y are perpendicular, x and z are also perpendicular, and y and z are perpendicular as well. Now you may say, okay, how did you name these x, y, and z? Is there a convention? Meaning, could I name z, y, and then y, z? Is it possible? Okay, these are not that arbitrary. There's a rule to find those, and you will actually find that rule really useful, and you're gonna see it in many places in physics. It's called the right hand rule. Okay, not the left hand, but the right hand. You use the 3 fingers of your right hand. These 3 fingers: thumb, index, and middle fingers. And there are many different ways of doing it, but just one way I find practical is call your thumb X, okay? And then the index finger Y. And then this will be the Z axis, okay? So X, Y, Z. So wherever you pick your X, put your thumb in that direction. You do it as well when you're watching this. X to the right, Y up, and the 3rd finger, middle finger, points towards you, right? Coming out of the paper or the screen. That's how we determine Z. So if I start with an X here and Y there, which way is Z? Is it up or down? How do you find? Use the right hand rule. Put X in this direction and Y in that direction, and Z points up. Okay, so you can use the right hand rule, not the left hand, but the right hand, right, to determine how to label these axes, X, Y, and Z. Anyway, so if you're in 3D, let's go back to the first one that I just drew here, a point in 3D space. Of course, you don't have 4 quadrants anymore, you have many, okay, like 1, 2, 3, 4, 5, 6, right? 1, 2, 3, 4, 5, 6, 7, 8. Did I count right? Anyway, so you pick a point here, and you can project this point onto the y-axis here, like that. So this will be a number here, and then you can consider this line here, which is along a surface or in a surface which is parallel to the xz surface. So you can find where that is over there. So this line here is parallel to that line, but this point now is on the xz plane, and it will have a projection onto the x-axis and onto the... You're still talking about rectangle. It's still rectangular coordinate system. This is how you find your x, y, and z. All right. So it's still these variables. In this case, 3 numbers define a point in the 3D space. So these are called rectangular coordinates. And how does it relate to the idea of vectors? Okay, you probably already guessed. So if you think about a line that joins the origin to that point, okay, and make it like an arrow, there's your vector. So that's how you relate your arrow description. But now you have numbers, all right? So these numbers, how does it give me things like the direction or the length, also called the magnitude of a vector? So let's worry about that for now. Let's talk about that. So, and by the way, this is not the only coordinate system. We have another coordinate system called polar coordinates. So one of many different coordinate systems. One of them is rectangular, the other one is called polar. So let's stick to 2 dimensions for now. Let's go back to our xy axes. So I have a point here, point P, given by these 2 numbers here, point X and point Y, right? Now, two numbers define a point uniquely, but do they have to be these X and Y? What if I keep the x-axis and keep my 0 as my origin here. So I want to find that point P, which was over there, right? I mean, I did not move the point. I'm just getting rid of the y-axis. That's what pretty much I'm doing here. So what two numbers can I use to determine that point P? Again, it won't be x and y anymore because there's no y. But what do I know? I know how far I am from the origin, right? So this line here, the length of this line segment here, I'm going to call it R, following the same tradition in the previous video, right? R. Well, that is a good start, because if I'm R away from it, that could be used as one of those two numbers required to define the point P. But think about it. I mean, you can remain R away from the origin, but you could be anywhere along a circle around the origin, right? These points are all possible because they're all R away from the origin, but I want that specific point, particular point. So how will I find that one? Well, for that I need a second number, and we choose that as the angle between this R and the x-axis. This angle right here, call it theta, all right? And we measure this theta from the positive x-axis in a counterclockwise fashion. Theta increases, all right? So maybe I should put a little arrow here to show that theta increases in a counterclockwise fashion. But now I have found my two numbers, right? These are R and theta. Whether I use x and y or the pair that is R and theta, P is the same point, just described with different numbers. So this one I'm going to call the polar coordinate system. Polar. So the origin acts like a pole and you're going around that. So it's a polar coordinate system, where the one on the left is called Cartesian, as you know. Cartesian, okay? But the thing is, the point doesn't change. And that point is where my arrow points at. The tip of the arrow is where P is, and the tail is at the origin, right? So it would be nice if I could go between the two. And that's very useful to understand vectors in this formalism. Starting with x, y, how do I find the corresponding r and theta, or vice versa? Given r and theta, how do I get x and y? It's very easy actually. Just need to remember that this r here, which is the length of the line segment that joins O and P, is right here, this point over there. And by definition, rectangular coordinates means right angle. So this is a right triangle. Okay? So this is point 0, this is point x. The physical distance that you can measure with a ruler, which is always a positive number, is nothing but x minus 0. So that is the length x. Okay? So this side is x centimeters or meters long, whatever your unit is. I'm gonna make another video about units as well, but that's something you can measure in inches, for instance. Similarly, along the y direction, y minus 0, which is y, is the actual length of that line segment. Okay, so make sure you make that distinction here. I call the points on the line numbers, whether they're called x, y, or z, and those numbers can be positive or negative or 0. It just tells you where you are on the line. But also now I'm talking about physical length, which is always a positive number. And to find that length, you subtract one of the number from the other one. Like you subtract 0 from x, that gives you the physical distance, all right? The absolute value of the difference of 2 points you can find on the line, if you will. But in any case, since these are rectangles, this side is also y. Okay, and then the hypotenuse, which is OP, line segment OP, hypotenuse and that is that you can find using the Pythagorean theorem, square root of x squared plus y squared. Very simple and basic, right? So that is what we called r. So let's write it as r. R is equal to square root of x squared plus y squared. Okay, that tells you how to go from Cartesian to polar, at least for one of the coordinates in the polar coordinate system. What about the other one, which is theta? How do you find theta? Well, theta in our right triangle is right there. This is your theta. Now you can use some trig here, trigonometry, and we have sine, we have cosine, we have tangent, right? Let's use tangent. Tangent of this angle theta is equal to side opposite divided by side adjacent, which means y over x. All right? So there you have it, a relation between xy on one side and theta on the other side. If you solve it for theta, that would be the arctangent, which you can write as a10 or arc10 or 10 to the power negative 1, any way you like. So arctangent of y over x. So given x and y, that's how you go to polar. Find r and theta. All right? And how do you go in the other direction? Given r and theta, how do you find x and y? Again, use your right triangle right here. Remember, hypotenuse is r. And we used already tangent. How about sine? What is sine theta? Or cosine theta? Now sine theta is side opposite, which is y, divided by hypotenuse, r. If you solve that equation for y, you get y equals r sine theta. And cosine theta similarly will be equal to x over r. Therefore, if you solve that equation for x, it is r times cosine theta. So there you have it. These two are your formulas for finding x and y given r and theta. That will be going in the other direction, from polar to Cartesian. Okay, really simple, basic rules. There are a couple of things you have to remember though. First of all, you got to be careful with the angle, all right? In this view, the angle is measured from the x-axis. So if we're talking about a point over here, P, where your 0 is over there, imagine the line that joins O and P, that is your R, yes, but the angle is now this angle, okay, an angle greater than 180 degrees. So as long as you measure your angles from the positive x-axis, these two formulas work just fine, okay? Just take your calculator, all right, and then make sure it's set to degrees, because it also measures in, calculates in radians, which I will talk about later, right? So just punch in your numbers, sine and cosine, you find the corresponding x and y, all right? Now, here's another issue though. What if you are given x and y, but you want to find the corresponding r and theta? Now r is easy, just square root of x squared plus y squared. But when you calculate theta, you got to be very careful, and this calculator will not give you the correct answer all the time, okay? Here's how. Here's how. Suppose you have a point here. Let's pick a point right there. This is your point, and then corresponding x and y values are 1 and negative 4, let's say. Okay, this is your x, this is your y, and you want to find r and theta. This is theta, this is r. Somebody said, how do you express this point? Using polar coordinates. So this is your goal, find r and theta. Okay, I mean, r, just use the square root formula. So you have negative 4 squared plus what? 1 squared. And you find a number, so square root of 17, right? That is 4.12. Fine, but what about theta? Now, if you go back to the formula I just wrote here, which is this one, let's see what we get. Imagine you find the arctangent of y over x, which would be 1 divided by negative 4. Okay, so let's do it. Shift arctangent negative 1 over 4. Okay, so you get negative 14.04. Okay, negative 14, let's say. Now, my calculator is set to degrees, so I can put a little circle here. That's in degrees. But is that 14 degrees? No, not really, okay? Is it negative 14 degrees? No, it's not negative 14 either, because this would be 14, and negative 14 would be below the x-axis. Negative meaning going clockwise, if you will. So what happened? Is your calculator wrong? Well, your calculator is not that smart, okay? You have to add 180 to it. All right, so add 180 degrees to that. That's 180. And that's because you're in the second quadrant. And you have to do the same if you are also in the third quadrant. For quadrants number 1 and 4, you don't have this issue. Okay, because you're not going to find the arctangent of a negative number. But for 2, I'm sorry, for 1 and 4, you don't have the problem of adding 180. But for quadrants 2 and 3, forget about the negative part. For quadrants 2 and 3, you have to add 180 by hand. So you add 180 and you get 165.9. So about 166 degrees, and that is indeed our theta. Okay, just something to keep in mind when you're going from Cartesian coordinates to polar coordinates. If you are in either the second or the third quadrants, you have to add 180 to what you find using the calculator, I mean the arctangent. All right, okay, so this is just, these are two of many coordinate systems. Now, this is very useful for our main task, which is vectors. Remember, we want to find a representation for vectors, which is called the coordinate representation. Coordinate or component, as it is called, component representation. To describe a vector A without referring to, you know, what I will measure using rulers or protractors, without drawing really accurate arrows on a paper, can I still do operations with vectors? So just like I needed two numbers in the Cartesian coordinate to describe a point P, if that point corresponds to the tip of my vector, I will need two numbers to describe my vector. So describe A describe or determine A with two numbers. Okay, so we're going to call these components, called components. Starting with a vector. Now, for now, I'm going to draw it just to describe you what the method is. But once we have this established, I don't need to draw it every time, right? Given a vector A, can I uniquely determine this vector using just two numbers? That's the idea. And we've already seen the coordinate axes. So let's start with that, okay? Can I come up with two lines to describe this vector? Now here's where I'm going to use the addition rule, okay? The addition, graphical method of addition. So these two components, could they be vectors? Let's start with that idea. Let's entertain this idea here. So can I write A as the sum of two vectors? I'm going to call it A1 and A2. It has two parts, right? A1 plus A2. If I know what A1 and A2 are, I know A this way, like going backwards. Forwards would be given A1 and A2. How do you find the sum? I'm looking at the problem the other way around. Given A, can I find two vectors? When added, they will give me A. Okay? I mean, if you think about it, there are many ways to do it. Here's one. You just have to use the graphical method rule. Here's one. A1, and then just line it up like this. And there you have it. A1 plus A2 gives me A. But is that the only pair? Not at all. How about this one? These two. How about these two? Now you quickly realize that there are actually infinitely many pairs like this. Alright? When you add them up, you will get A. So it's not really that useful, okay? So I'm gonna start putting conditions on it. What if I have a condition? Let's say the two arrows are perpendicular to each other. Okay, let's try it. So I start with this A again. Now I'm gonna pick two vectors which will form my pair, but they can't be at random angles like this. They have to be at 90 degrees. Okay, so the two vectors that are 90. Okay, how about these two? Okay, well, if those two work, well, these two work as well. When added, they give me A. But a quick study shows that, I mean, you can still find others. Like, how about this one? This one here, and that one. All right? And if you keep doing this, I mean, the rule is 90 degrees apart. These two are. But I already found different ways of doing it, so it's still not that uniquely defining A. There's still infinitely many possibilities. So what do? I impose one more condition on it. I say one of the lines have to be horizontal. If I do that, then the only option is this, and that corresponds to this, which is also that. Remember, this one is equal to that. They're just parallel transformed versions, okay? So these line up along my XY directions. So I'm going to stick with these two, okay? Because I know that when these two are added, they give me the vector I want, which is A. But these are just along these two axes called X and Y. All right, but keep in mind, I mean, it's up to you to pick where X is. You can rotate X, Y will rotate accordingly. And your XY is not better than someone else's XY. All right, I mean, you have the common origin, but you may have different coordinate axes. So there's still some choice left to you. But if I write it like this, these two are called the component vectors. And instead of calling them A1 and A2, I'm going to call it AX and AY. Okay, so this is the vector AX, and this is the vector AY. So A is written as AX plus AY. Alright, these are called the component vectors. As you can imagine, if you're in 3D space, you would need three vectors, AX plus AY plus AZ. I'm going to draw a picture of that too in a second. So these are called the component vectors. This is the this is the vector we started with. Alright, so these vectors, meaning the component vectors, their directions are arbitrary. The directions are along the y and x axes, but their magnitudes, all right, their magnitudes, which we can write as ax, put the bars next to it. Now we're talking about a scalar, a positive scalar, ay here, magnitude. These correspond to the lengths of, or the sides of the triangle. Which triangle? The right triangle we have here. Now you see how the connection between polar and Cartesian coordinates is going to help us now. We have the angle here, theta. We had right angle there, right there. So AX magnitude is just the adjacent side to theta, and AY, if you think about the rectangle, these two sides are equal to each other. The length of AY, the magnitude of AY, will be the side opposite to the angle theta. All right? These are positive numbers. But we also have the coordinates. Remember, this point here corresponds to a pair of numbers, which are x and y, which you can find along the axis, the projections. But no, those numbers are nothing but how far you're away from the origin. So call this point your unknown x, and this is point 0. So that specific x minus 0, which is the positive number that you're looking for, that's nothing but the length of ax, right? So it doesn't hurt if I replace that x here with the number a sub x, and here this point is what I call really ay, okay? Not the vector, the magnitude of the vector, okay? That is the scalar ay. So I'm going to call those the components. Ay and ax are called component, not component vector, but just the components. All right, components. So sometimes you can use the notation here, a vector, you use parentheses and then write ax here, comma, ay. I don't use this notation that often, but it's in the books, okay? Ax, comma, ay, that still represents a vector, and you will sometimes even see this one instead of brackets. I mean, instead of parentheses, you will see brackets like this, ax, ay, okay? That also means a vector. It just depends on, you know, who's writing the book, basically. I will not use these that often. Actually, there's a better way, better notation. I'm going to use that, which is called unit vectors. But yeah, that's the components. Simple as that. So if you have a vector pointing in the, if you have a vector in the fourth quadrant, remember the fourth quadrant is here, right? So if you have a vector in that direction, this means you have a negative ay and a positive ax. Okay, now by ax and ay, I'm talking about the projections of those 2 points. And if a vector is not, if the vector doesn't start at the origin, does it make a difference? Let's say this is the origin you already have, and then somebody just draw an arrow here and call it B. Okay, what are the components? Are you gonna just draw a line from the tip and call this point on the x-axis bx? No, you can't do that because the tail of that arrow doesn't coincide with the origin. So you either take B all the way to the origin, or without doing that you can just drop this point all the way to the x-axis. So you find these 2 points, call them x2 and x1, and take the difference x2 minus x1, and that will be your bx. Okay? Now this will make much more sense when I show you how to add or subtract vectors using this component method. Okay? But basically you want to find this vector here. Okay, this vector. This is your by component vector. Alright? So, before I show you the addition and subtraction, let me try to draw this in 3D. Okay, so here you have. Oh, by the way, if you have A written as ax plus ay in this manner, this means the magnitude of A, remember the polar coordinates now, how we found the hypotenuse, the same way. The length of ax squared plus the length of ay squared, so where ax stands for, now it stands for the length of the component vector. It also stands for the coordinate itself, or the component itself. Okay, so in that sense, I mean, this is what we used before, but this is more general than that. So in this formula, ax can be negative or positive, possible. In this case though, ax was always positive, because that notation. That's why I usually prefer the bar notation when I talk about the magnitude, okay? If I don't write the magnitude symbol, those bars, it may be ambiguous, you know, am I talking about the component itself or the length of the component vector? The length of the component vector is always positive, but component itself could be negative or positive. You just saw it here, up there, right? The component here was negative. So just keep that in mind, but the formula here works with actual components, so the numbers can be negative as well. So let's just draw an arrow here. This is our 3D vector. So what will be the corresponding ax, ay, and now we have az. So let's pick our x, y, z using the right-hand rule, remember? So if this is your x, this is your y, so x, y, and z, this will be your z. Okay, so these are the projections and rectangles that you encounter when doing that. If you draw your vector now, this is your az, this vector here, component vector az, and this will be your ax, and this vector here will be your ay. So a can be written as ax and ay and az all added. Alright, now if you have a hard time visualizing this or justifying this, you can always do it by parts, meaning why don't you add ax to ay first using the parallelogram rule. Ax plus ay is this vector right there. Okay, this is just ax plus ay, if you can read that. Ax plus ay. Now once you get ax plus ay, you can forget about the xy axes and the ax, ay vectors. Just think about the plane that is formed by az and ax plus ay, and draw the parallelogram created by those two vectors. You end up with your a, okay, because you have your rectangle here. So it proves that a is indeed the sum of these three vectors. Okay, so this is the component representation. Now let's go back to 2D again, because it's easier to draw things in 2 dimensions. Let's see how the addition rule we already know, meaning the graphical addition, how does it work with the components. So let's take two vectors, a and b, and let's add them up. So I'm going to draw them already lined up like this, a and then b, like this. So from the rule from video part 1, we know that a plus b, which you can call c if you like. Let's write here, c is defined as a plus b. C will start from the origin just like a, but it'll point at where the tip of b is. So this will be your a plus b, which is c. All right, so that's the graphical representation. How does it relate to our components? Now we just need to find where those components are. Start with a, draw a line here onto the x-axis. This actual point here is a x, and this point on the y-axis is a y, which means that the physical length from 0 origin to the coordinate ax is actually ax. Now I'm talking about the length of this vector, right? So you know what I'm talking about. So this one is now lengthwise also ay. So you can apply the same logic to b now. B, meaning draw a line perpendicular to the x-axis, the projection, and recognize this length as the length of the component vector bx. Similarly, if you draw a line which is parallel to the x-axis, so you find the y projection here. So this side here is the length of the component vector by. All right, but there's also c now here. So this length from here to there, from 0 to this point, now I can call this the component cx, and this point right there. Remember, these components can be positive or negative, all right? I'm going to stress that many times. Those can be positive or negative. The physical distance, which I use with bars, can be positive, are always positive. But this sub here, which is cx magnitude, and here, this is the length of the component vector cy. Now obviously cx is equal to ax plus bx, okay? Now that gives actually a good method of adding vectors and finding the components of the resulting vector, but it kind of looks restrictive, like I picked vectors which are both in the first quadrant, okay? Does it work for vectors pointing in different directions? Let's say I have the first vector a still pointing this way, but now the second vector, let's say like this. This is your b. Now obviously b has a negative x component, right? So how do I find the components of the resultant vector? It's called the resultant vector. A plus B, which is C. Now I'm going to get a negative component for C, right? So this Cx will be negative, and Cy is still positive. So if I want to really find the coordinate, I don't really think in terms of the lengths of the component vectors. That's very restricted because they're always positive. But in this case, I may end up with negative numbers. So I just write it like this. Cx is equal to Ax plus Bx. Because I know that Bx is a negative number. If I carry B, if I parallel transport it to the origin, I will end up with this vector here. I know that already. It's parallel transport B, and B has definitely a negative x component. I know that. So if Bx is negative, I'm subtracting that number from Ax. That's how I find the negative number, which is Cx. Same thing about Cy, okay? Cy is equal to Ay plus By. So basically, these two equations are nothing but this compact equation, C equals A plus B, written explicitly. Whenever you see a vector equation, keep in mind that it is really two or three equations. 3 meaning 3D, x, y, z, all right? So the compact form may look like just one equation, but it is always multiple equations, because when you write them in terms of the components, you add or subtract if you have a third vector, a fourth vector, D, which is A minus B, then the components of that vector can be written as Ax minus Bx, and dy, the y component is Ay minus By. Okay? So again, one compact equation with the arrows on the top, a vector equation, are actually nothing but these two equations. Always keep that in mind. Vector equations are equation systems, multiple equations, systems of equations. So, that's all. That's how you add vectors in the coordinate representation, or the component representation. All right? So, let's apply this to a practical problem of a map. Okay, distances on a map. Let's say on the map here, you open it up, and then you're making a trip, plans for a trip. Okay, you start from here, Houston. You start at Houston, and you're gonna go to Austin. What I call it, Austin, and from Austin you're gonna go to Dallas. All right, so you know that to go to, of course, the highways are not straight, but for our purposes, we're using, bird's eye view, or maybe it's a plane. You're just flying a plane, and the directions are north, pointing this way, south, and east, and west. All right. Now I'm gonna make up numbers. All right, which is not a good thing, but let's just make up a number here. Let's say this is from Houston to Austin. How many miles? Okay, unfortunately I don't know how many miles. I'm just gonna make up a number. Okay, 200 miles. And from Austin to Dallas, let's say it is 250. These numbers are probably wrong, but doesn't matter. Just Just trying to make a point here, right? So to go to Austin though, you need to fly in a direction which is, let's say, 65 degrees west of north. So you just have this angle here. This was north, right? So 65 degrees west of north. And to fly to Dallas from Austin, you have to, let's say, this direction is 40 degrees north of east. All right? So, given these numbers, can you find where Dallas is with respect to Houston? Meaning, find me information about this vector now. That is indeed the resultant vector, right? Call this vector, I don't want to, what do you want to call it? R, what's called V. Now V stands for velocity. Let's not use V. Let's call this A. Oops. Let's call it A. I'm going to call the vector by the destination name A. Therefore, this will be called D. So I'm trying to find this vector now, which is A plus D. So find the length of A plus D, which would be the Houston-Dallas distance. Find the magnitude of A plus D. And also find the direction. Okay, find the direction, meaning an angle. Probably an angle you would measure from the eastward direction. All right, so very basic vector addition problem. I'm just gonna find out the components first of A and B. All right, so let's start with AX. Given A, what is the corresponding X component? Now you can tell right away. I mean, if this is the west direction, that's my negatives here. These are my positive in the east. Similarly, north is positive, south is negative. The center is the origin, right? So AX will be a negative number in that picture. Okay, so think about the triangle here. Always locate your right triangle to determine which angle you're using. So if you're, draw a box around, okay? Draw a box around the vector A. It always works. Draw a rectangle around your vector, just like that. And identify your sides as your AX and AY. The lengths of the sides will tell you. For instance, if you want to find AX, you want to solve for this side here, which is the horizontal, okay, the length of the rectangle there. So obviously you'll need this angle 65, and the side we need is side opposite to 65. So the hypotenuse multiplied by the sine of 65 gives me the side that I need. All right, so multiply 200 miles by sine 65. This will give me this side here. But I know that AX is a vector pointing to the left because of the direction of A. Therefore, I put a negative sign in the front. That will be my AX. Now for Y, I don't have that problem, right? AY is positive, which is 200 miles times cosine of 65. Now what about D? Think about D. dx and dy are both positive because D is a vector that points in the first quadrant. Just draw your box around again. If you're ever in doubt, draw your box around it and identify the sides of that rectangle as your guidelines. Okay, so dx will be the length of that triangle, and it's positive. So 250 cosine 40, right there, cosine 40. And dy will be 250 sine 40. All right? That would be this side here, or this, which is equal to that one. So find those numbers using your calculator and then add them up. Add ax to dx and add ay to dy. So if you do that, what do you get? Let's see. dx plus ax, or ax plus dx, doesn't matter, and ay plus dy. So let's find these numbers. Make sure your calculator is set to degrees, not radians. So 250 cosine 40 minus 200 sine 65. That gives you 10.25. Now you may say, why are we including 2 digits after the decimal point? Well, not for any specific reason, okay? I mean, the topic of significant figures is for some other video. Let's not worry about that, okay? There's not really a particular reason why I picked 2 decimal points after digits after the decimal point. So ay plus dy, so 250 sine 40 plus 200 cosine 65, and that gave me 245.22. All right, okay, so this vector is indeed pointing in the first quadrant. I can tell right away by the signs of these two components. Both are positive. What about the length of a plus d? This will be the physical distance between Houston and Dallas, or hypothetical cities here, because I made up those numbers in the beginning. 245.22 squared. Okay, so this number squared plus 10.25 squared, and take a square root of that. 245.44 miles. What about the direction? Now I'm talking about this angle here. Call it phi. All right. Now that angle can be found. Remember the polar coordinates business? Same thing. Phi will be equal to arc tangent, the y coordinate divided by the x coordinate. And 25. So 245.22 divided by 10.25. Take the arctangent of that, 87.6 degrees. That is the direction. Keep in mind, if your resultant vector, if it was pointing in the second or the third quadrants, you would add to this number that you find using your calculator 180 degrees. You would add that number to get the exact correct number. So this is 87.6 degrees north of east. North of northeast. Okay, a very basic application of vectors or vector addition using the component method. All right. Now, there is another very useful tool which is called the unit vectors, or the unit vector representation. Unit vectors. Unit vector means the length of the vector is 1. a unit vector, whatever that is, has a length of 1. Okay? Remember how we add the vectors, or let's say, remember how you multiply a vector by a scalar? So given A, the vector 3A would be 1, 2, 3, a vector pointing in the same direction, but 3 times longer, right? And that's because we carry this A to here and to here. And using the addition rule from the tail of the first to the tip of the last, you find the resultant vector, which is just multiplication by a scalar, 3, in this case. Now, what if you multiply a vector, or let's say, what if you multiply the length of a vector by this unit vector of ours? Meaning, if I could find a vector, or if I could come up with a vector in the same direction, okay, I'm going to call it U. U stands for unit vector, and U, vector U, has a length 1, just following the same definition. How many U's do I need to add to find the 3A vector? Okay, whatever the vector is, or even A. How many U's I have to add like this to find any of these vectors? So A is going to be written in terms of the unit vector U. Well, the length of A has to be multiplied by U. Simple as that. The length of A, if you multiply the length of A by that unit vector, that's what you get as A. In this case, I have 1, 2, 3, 4 of them, but it could be any number. It just depends on how long it is, right? So using this idea of expressing any vector in terms of a unit vector in the same direction, I'm going to go back to my component representation with the x and y component vectors. Remember? This was the x and y axes. And I had this vector here. Let's use a different letter this time. Let's use B. Okay, you're bored with A. Now, this vector B has 2 components, component vectors. One along the x direction, which we name as Bx, and another one along the y direction, which we call by, because if you add them, you get b. We know so far. So what if we decide to write bx and by vectors, just like this one, in terms of unit vectors? I'm not going to call it u now. I'm going to call them I and j. Okay, so I will be the vector along the x-axis, and j will be the vector along the y-axis. And since these vectors have unit length, this vector I'm talking about, along the x direction, I, and along the y direction, j, but their lengths will be equal to 1. So not any vector, but specific vector. Just to remind myself that these are those specific vectors, I'm not going to put an arrow on the top. I'm going to put a hat, like this, j hat and I hat. So I hat is the unit vector. Its length is equal to 1. J hat is the unit vector. Its length is equal to 1. All right? I don't know why I put a dot there. Let me fix it. Okay. All right, I hat and j hat, that's what they're called. So in this formalism, bx, the vector bx, the component vector, is nothing but, now for this case it's pointing in the x direction, so I could write it as the length of bx times I hat, which is correct, but in general b can point in any direction. If you take that into account, it's better to write it as this, bx, the actual component, times I hat, because it could be pointing to the left, right? I hat always points in the positive x direction, but if your bx points in the negative x direction, that takes care of that, all right? Similarly, by points in the positive, points in the y direction along the j hat direction, so I'm going to write it as by j hat. So combining the two, okay, I mean you can scratch this one, you don't need that. This is the one you need, these two are. So any vector can be decomposed into its x and y components with the use of unit vectors, like this. Remember what I said when I don't really like this notation this much, the parentheses notation. I don't use it that much. Here's the reason, there's a better version of it, okay? I like the one with unit vectors, bx. If you are in 3D space, like we had before, where was it example? The 3D, let's try to write this now in 3D. Right there, this vector. So here A will be ax I hat plus ay j hat, but now there's az, which means I need a unit vector in the z direction as well, and that I'm going to call k hat. So plus az times k hat. Okay, any vector can be decomposed into its x, y, z components using the unit vectors. Now when you're doing algebra with these vectors, make sure you always carry I, j, k hats along with you. Never drop them, never lose them, otherwise you'll make a big mistake, okay? Meaning this, if you have three vectors, b and c, and you want to find 2a minus c plus 3b, for some reason you want to calculate this vector, which is also a vector, you can call it d if you like, doesn't matter, but it's a vector. So what do? You, in order to find, okay, let me move it to the right a little bit. So if you want to do it component by component, you know what to do, that's easy, right? So dx will be 2ax minus cx plus 3bx, and then you do the same thing for y and z, etc. But if you just want to take the vectors which are given in terms of unit vectors, let's say a is 5 I hat minus 2 j hat, b is 6 k hat minus 2 I hat, and c is 3 j hat. You can directly plug those into that equation. You can take these and plug all of them in this equation and find exactly what d is, but that make sure you keep those placeholders, which are I, j, and k hats. Okay, never lose them along the way. But when you're adding them, whatever is in front of I will be added to the other number in front of I hat. Okay, so in this example then, let's take care of this real quick. So the result, d, will have an I term plus a j term plus a k hat term. In the I hat term, you need, okay, which of them have I? You have 1 here, and you have negative, where is I? This was I, right? Negative 2 there. Okay, so 2a means 2 times 5, 10. All right, and then c doesn't have any I. 3b plus 3b means negative 6. All right, and then the others are done the same way. All right, so this is the unit vector representation, which is quite useful. Any vector can be decomposed into x, y, z components and unit vectors. In some books, you will see an alternative notation. It's the same thing written differently. In some books, you will, instead of I hat, you will see x hat. And ay plus y hat plus az times z hat. Okay, so please don't be confused. It means exactly the same thing. Now, using this system, we can come up with a way to multiply vectors. Okay, vector multiplication. But let's leave that for another video. I'm gonna stop right here. Okay, so till next time, goodbye.